You've got this super genius AI, right? It knows practically everything. But then you try to teach it just one new thing, and suddenly it's this super expensive, super slow process. It's actually one of the biggest headaches in AI today. So what if there was a smarter way, a more efficient way to give these massive models new skills? Well, that's exactly what we're going to dive into.
All right, so here's the game plan. We're going to walk through this whole story, starting with the big problem, then a clever shortcut that turned out to be flawed. And then we'll get to the new fix. We'll look at why it's so pricey to train AI, check out this brilliant method called LoRA, see where it falls short, and then meet its successor, DoRA. And yeah, we'll get real about the pros and cons and what it all means.
So, first up, the billion-dollar update problem. Let's talk about why teaching AI is so ridiculously expensive.
Okay, so I want you to picture one of these giant AI models, right? The ones with billions of parameters. Think of it like a super complex, high-performance car engine. Now, if you want to teach it a totally new skill, let's say switching from writing poetry to drafting legal contracts, it's like you have to rebuild that entire engine from scratch. Sure, the result is powerful, it works great, but man, the time, the data, the sheer computing power it takes, it's just massive.
And that old school method? That's what we call full fine-tuning, or FFT. And look, it's the gold standard for a reason. You get the best possible performance, no question. Because you're tweaking every single one of those billions of parameters, the model really, truly learns the new thing. But here's the catch. For most people, and honestly, even for a lot of companies, the cost is just insane. It's totally impractical. And that's what forced everyone to start looking for a much, much more efficient way to do things.
And that brings us to our next chapter, LoRA, the efficient shortcut. This was supposed to be the first hero of the story. The idea behind LoRA is just genius. Instead of rebuilding that whole engine, what if you could just add a small, high-performance tuning chip? That's LoRA. The original engine, all those billions of pre-trained parameters, you don't touch them. They're frozen. Instead, LoRA just slips in these tiny, trainable adapter modules, and you only train those. We're talking about updating maybe less than 1% of the total model. And just like that, fine-tuning an AI became something that pretty much anyone could do.
Let's take a quick look under the hood to see how this works. On one side, you've got the massive original model weights. What LoRA does is it injects these two teeny tiny matrices. You can see them here as A and B. The data flows through them, and whatever comes out gets added to the main model's result. The key thing to get here is that we are only training A and B. That's it. It's super elegant, incredibly efficient, and because you can just pop these adapters in and out, it's modular. It's no wonder this thing completely took the AI world by storm. Okay, now for the plot twist. LoRA seemed perfect, right? But there was this nagging little problem. For all its amazing efficiency, it just couldn't quite match the performance of a full fine-tune. There was always this small but consistent performance gap. And for the longest time, nobody really knew why. So why? Why was there this gap? The common wisdom was, well, duh, you're training way fewer parameters. And that makes sense, right? Less training equals slightly worse performance. It seems totally logical. But it turns out that wasn't the real story, not even close. When researchers started digging into how the updates were actually being made, they found something pretty unsettling. The big breakthrough came when they realized you could split the updates into two separate parts. You have magnitude, which is basically the how much part. Think of it as the strength or the volume dial for a connection in the AI's brain. And then you have direction, which is the which way part. It decides which connections to change and how they should all work together. And this, right here, is the absolute key discovery. It turns out that during a full fine-tune, the model learns to change magnitude and direction independently. It can crank up the strength without messing up the direction, and vice versa. But LoRA couldn't do that. Its changes were coupled together. When it tried to change one, the other would change too. It was like trying to steer a car and control the gas pedal with the same single lever. And that was the real reason for the performance gap. So, once they figured out the problem, the solution became pretty clear. They needed a smarter way to update the AI, one that could fix this flaw by separating those two jobs.
And that new method is Weight-Decomposed Low-Rank Adaptation. Yeah, it's a mouthful. Thankfully, we can just call it DoRA. It came out in early 2024, and it was designed from the ground up to fix the exact problem that researchers had found in LoRA.
And just to get this out of the way, no, not that DoRA. But hey, this DoRA is definitely an explorer in its own right. It's exploring much better ways to fine-tune AI. It's a clever name for sure, but the tech behind it
is the really cool part. So, how does DoRA actually work? It's a really smart three-step process. First, it takes one of the model's original weights and basically splits it in two. It decomposes it into its magnitude and its direction. Step 2, it creates a brand new, separate thing that's only responsible for tuning the magnitude. And for Step 3, it uses our old friend LoRA to do what LoRA is already good at, updating the direction. See? It gives the model two separate tools for two separate jobs. Simple as that.
All right, so DoRA works. It consistently beats LoRA and gets us much closer to the performance of a full fine-tune. But, and this is a big but, there's no such thing as a free lunch, especially in engineering. There are always trade-offs, and it's super important to know what they are.
Let's talk about one of the biggest ones, memory. During training, DoRA can be a lot heavier. Take a look at this chart for a CNN model. Those are the kind often used for images. DoRA's peak memory usage is almost 50% higher than LoRA's. That's a huge deal if you're a developer trying to train on a machine that doesn't have a ton of memory to spare.
So let's break down the key trade-offs you got to consider. First, it's slower to get started. That whole decomposition step, it takes time. A LoRA model loads almost instantly. A DoRA model can take a few minutes. Second, like we just saw, it uses more memory, especially on models that aren't transformers. And third, and this one is a real deal breaker for some folks, especially in the generative art scene, is the stacking problem. You know how with LoRA you can just mix and match different adapters, like one for a character's face, one for an art style? Well, you can't really do that with DoRA. The math just doesn't work that way. That loss of modularity is a major, major drawback.
So where does that leave us? We've got better performance, but we've also got some serious trade-offs. Let's talk about the future of AI adaptation.
Okay, so here's the bottom line. LoRA is still the king of speed and flexibility. It's fast, it's light, and it's plug and play. DoRA, on the other hand, is the new champ when it comes to pure performance. It gets you way closer to that full fine-tuning gold standard, especially when you're trying to be super efficient with a small adapter, which is where LoRA really starts to struggle. So really, it's not about which one is better, it's about picking the right tool for the job you're trying to do.
And all of this leaves us with a really fascinating question, doesn't it? As these AI models get bigger and bigger, what's the path forward? Is it about finding even smarter ways to decompose them like DoRA does? Or will we eventually find a way to make them so smart that they can just learn and adapt all on their own? Something to think about.